Okay, let us now see one more example of a transformation. In particular, let us focus on the following composite function. So, we start with our function g of x, which is by definition, well, the 2x that you already seen previously. And we want to, the second function is going to be f of x, which is our mountain function, 1 minus x squared. Our goal now is to compute and get the graph for the function f of g of x. Schematically, what does that composite look like? Well, if you give an x here, you first compute g of f, g of x. So if you start with some x that you choose, you first compute this thing with g, giving us, well, what's written here, 2x. After you get your 2x, now f(x) on that 2x. So on that 2x, now f(x). Well, and what does f does on x? Well, it computes this thing. So where is x? Now we put 2x. So f is going to map 2x into 1 minus 2x, whatever that 2x is going to be. So this is schematically. Let's now draw the graph for these two functions. This function g is a line that contains the point, the origin point, because if x is 0, then 2 times 0 is 0, so the point with coordinates 0, 0 must belong to this graph. If you choose x is equal to 1, then 2 times 1 is 2, and so the point with coordinates 1 and 2 must also belong to the graph of this function. So this is a line, so the 2 points determine a line, and the line is like this. So here is our function. Let's now go to this one. We already seen this before. And, well, the zeros of this function are here, -1, and 1 here. When x is 0, the function takes the value 1, and so it is our mountain function, like so. Can you see? Well, if you keep on going with the axis, this thing goes down and goes down up to minus infinity. What does it look like, the graph of this thing? This is our question. What we want? How do we get this thing? And what does it look like? Well, to get the graph of that thing, we could, for example, choose some x's, just like we did for the other example, choose some x's, compute the y's, and then try to guess what the function looks like. But instead, I'm going to do it in another way, which will give us more insight in what happens during this transformation. So instead of feeding values into this machine, which you could do, I'm going to instead feed a set of points. In particular, let me put in green. In particular, let me choose the set of points that goes from -1f up to 1f, excluding the -1f and 1f. Okay? Now, g acts on this set of points, on each one of these set of points, and multiplies each one by 2. Graphically, what does this mean? Well, the set from -1f up to 1f is this set here, open. So -1f up to 1f. So this set is this set of points here that live on the horizontal axis. And on each one, now f acts, giving us in red, well, let us see, -1f would be mapped into -1, like so, but it's open. The 1f would be mapped into 1, but open. And all the intermediate axes between -1f and 1f would be mapped to these intermediate points here. Let me say it again, because in case you can see. This first point is mapped into here, the second point is mapped into here, then into here, the 0 is mapped into itself, because 2 times 0 is 0. Then the next point is mapped into this one, this point is mapped into this one, the red one, and finally 1f is mapped into 1. But though you see 1f is not included in the set, so 1 is also not included into this image set. So the image set goes from -1 up to 1, excluding the endpoints. So this is how G acts. Now in turn, f acts on this set of points. So let's do this graphically. Start by drawing this set of points that goes from -1 up to 1. So it is this set of points here, this set of axes. F will act on each one of them and give us, well, graphically it's easy because this point is mapped into this point is mapped into this point is mapped into this point, and so on. In particular, 0 will be mapped into 1, and so on. So this set of inputs is mapped, inputs for f, is mapped into this set of outputs. Now, let us see. How do we see the graph of this thing now? Because it is the composite function. And so the composite function, well, it's here. Is this entire thing, this entire block, acting on that set. So the entire thing acting on that set gives us, well, that set. The set of images here on the arc, which, by the way, goes from 0 up to 1. Can you see? The set of y's here on the arc goes from 0, but excluding the 0. Can you see? Up to 1, including the 1, because the top of the mountain is included on this thing. So the composite here assigns this axis into these y's. Now, what the idea is going to be to draw these ordered pairs, where the first entries of those ordered pairs are these x's, and the second entry are those y's. Let me first draw here the first part of these ordered pairs, which is the axis that live between -1f up to 1f. So it goes like this: open and open. So this is -1f and 1f. You already draw this thing here, are the set, each one of these points that I'm marking are the entries, the first entries of these ordered pairs. Now, what are the second entries? The y values, well, are those living in between 0 and 1. Graphically, that means that the first point here in green must be assigned to this point here, the next point here is assigned to this one, and so on. In particular, 0 is assigned to 1, and then this point is to this one, and this one to this one, and so on. Can you see how the ordered pairs between here and here are assigned? Because now it is evident from a graphical point of view what we have to draw. Because if this point is attached to this one, well, you should draw it above it. If this point is attached to this one, you should draw it above it. If this point is attached to this one, you should draw it above it. If this point, the 0, is attached to this point, this should be drawn a bit more carefully. If this point is attached to this point, you should draw above it. If this point is attached to this point, you should draw it above it. Let me just do it like so. If this point is attached to this one, you should draw it above it, and so on, here. So essentially what you get is this curve here. Okay? Can you see? This should be a bit more You should be more careful drawing this thing. But you see the idea. This is the important thing. Is that this set of points are attached to this set of x's must be attached to this set of y's. And when you draw this thing, well, we have to draw the y's above the x's, but as a result, you need to shrink, essentially. You should have to shrink the graph in blue into this black one. And that is the effect of this composition, of this transformation. So when you start with a function, so in conclusion, when you start with a function like this, and now you multiply the argument by some number that is larger than 1, just like 2 was, then the resulting composite thing now must be something that is smaller, so it is compressed through along the axis. Okay, along the axis. So it's compressed like this. Okay, can you see? And this is the main idea of that I want to tell you. Okay, the main idea that now, of course, you can now think about, well, what if instead of 2 is 1f? What would happen? Well, if multiplying by a number larger than 1 shrinks the thing, well, probably multiplying by a number smaller than 1 will make it wider. But I leave that as an exercise. So you can run this argument again, but instead of 2, you do it 1f. And any number will work. Okay? So you can try many numbers, but you see, this is the main idea. Okay? And all this thing is based on the concept of the image of a set, because it's much easier to see the image of a set and see these assignments through sets rather than to individual axes that you feed into this thing. Okay, so this is the main idea, and well, the answer is given. Okay, now I would like to stress this idea of it with a little bit more. Okay, to run the argument probably from a different point of view. I'm going now to show you a video and explaining this thing a little bit faster, but at least a bit more elucidating, so that you can see it again in action. So let's see.